first time in U.S. history, NASA's OSIRIS-REx mission successfully captured a pristine 4.5 billion-year-old sample from the surface of an asteroid. This remarkable journey began in 2016 when the spacecraft set off on its mission to the asteroid Bennu. And in May 2021, it started a monumental 1.9 billion kilometer return trip to bring its precious cargo of asteroid rocks and dust back to Earth. 2 years and 4 months later, in September 2023, the spacecraft's sample return capsule re-entered Earth's atmosphere, blazing across the sky at over 44,000 kilometers per second hour. This milestone marks a groundbreaking achievement in space exploration and a leap forward in our quest to understand the origins of our solar system. Picture this. A cosmic time capsule carrying materials from our early solar system untouched for billions of years. What stories could these ancient rocks and dust tell us about the asteroid's origins or even the foundations of life itself? And what's next for the OSIRIS spacecraft? Stick with me as we uncover the awe-inspiring details of the OSIRIS-REx mission's triumphant return and explore the fascinating discoveries from Bennu's ancient treasures. After 7 years of planning, space travel, and data collection, OSIRIS-REx made its way back to Earth. Well, technically it didn't land, but passed by Earth just close enough to release its sample return capsule. At a distance of about 100,000 kilometers from our planet, the spacecraft released the capsule, sending it hurtling toward Earth's atmosphere on September 24, 2023. With precise calculations, OSIRIS-REx then fired its thrusters, avoiding a collision with Earth and embarking on an entirely new mission, but more on that later. The capsule's descent was a masterclass in precision. Entering Earth's atmosphere at just the right angle, it targeted a landing zone roughly 600 square kilometers in size, about the size of Chicago or the Isle of Man, in Utah's rugged desert. This maneuver had to be executed flawlessly, and it was. The capsule's journey through Earth's atmosphere was nothing short of extraordinary. Traveling at a staggering 43,000 kilometers per hour, it became the second fastest human-made object to re-enter Earth's atmosphere, just behind NASA's Stardust capsule. It endured an intense 32 G-forces, 32 times the force of Earth's gravity. For comparison, astronauts typically experience about 3 Gs during launch, and even the most hardened fighter pilots rarely withstand more than 9 Gs with specialized gear. Yet, this capsule was built to handle it. As it tore through the atmosphere, temperatures on the capsule's surface soared to approximately 2,700 degrees Celsius, half as hot as the sun's surface. Infrared trackers on the ground watched as it streaked through the sky, while the asteroid sample inside remained safe and cool thanks to cutting-edge thermal protection. This heat shield, known as PIXA, phenolic impregnated carbon ablator, worked by burning away its outer layers, a process called ablation that dissipated the heat and shielded the cargo from the fiery descent. Once it slowed down enough, the capsule deployed its first parachute to stabilize its descent. Then, about 16 kilometers from the ground, a radar locked onto its location. Finally, a second parachute softened the landing, reducing the speed to a gentle 18 kilometers per hour, about as fast as a cyclist on flat terrain. The entire descent, from atmosphere entry to landing, took just 10 minutes. The NASA recovery team sprang into action, retrieving the capsule by helicopter to ensure it wasn't exposed to Earth's environment. They transported it to a clean room where it was decontaminated before being opened. But even with all this careful planning, opening the sample canister turned out to be a challenge. Scientists at NASA's Johnson Space Center in Houston got their first glimpse of Bennu's material just weeks after recovery. The outer lid revealed an unexpected surprise: 70 grams of dark gray rocks and dust outside the main canister. While this bonus material was exciting, it wasn't as pristine as what lay inside. To access the main sample canister, scientists faced an unexpected problem. 2 fasteners were jammed with asteroid dust, requiring a new tool to be designed and built. 3.5 months later, NASA engineers successfully opened the canister, revealing 51 grams of untouched material. Combined with the bonus material, the mission returned more than twice its original goal. The samples were carefully cataloged and divided. At least 70% will remain pristine for future generations of scientists to study, while the rest has already been distributed to over 200 researchers worldwide. Why is this handful of asteroid dust so special? Imagine holding a piece of our solar system's ancient past, materials that predate Earth itself. Just over a week after recovering the capsule, scientists began analyzing the bonus regolith. Bennu, believed to have broken off from a larger asteroid billions of years ago, contains primordial ingredients that existed before the planets formed. The sample includes presolar grains, microscopic crystals older than the Sun. By analyzing these grains, scientists can uncover details about the stars that existed long before our solar system formed. Some grains suggest origins in small and medium-sized stars, while others hint at contributions from supernovae. Initial analysis also revealed that Bennu's dust is rich in carbon, nitrogen, and organic compounds, the essential building blocks of life. Even more intriguing, water-bearing clay minerals in the sample confirm that Bennu may have originated from a water-rich parent body. While Bennu itself isn't hospitable to life, its composition proves that the building blocks of life are abundant in the universe. This discovery echoes the sentiment of Carl Sagan, who once compared the emergence of life to musical notes waiting to be arranged into a symphony. Bennu's compounds might not yet form a symphony, but they provide invaluable clues about the chemistry that predates life. But the discoveries don't stop there. The presence of hydrated minerals suggests that Bennu's parent body was at least 10 kilometers wide, and possibly even a world with liquid water. Minerals like serpentine and peritite, commonly formed in the presence of water, point to a dynamic and active history. Even phosphates essential for DNA were found, offering tantalizing hints about Bennu's origins. So, what's next for OSIRIS-REx? After delivering Bennu's sample, the spacecraft ignited its engines, heading toward a new target, Asteroid Apophis. Renamed OSIRIS-APEX, Apophis Explorer, the spacecraft will reach its destination in 2029. Over 18 months, it will map Apophis, study its composition, and perform a daring maneuver, dipping within 16 feet of the surface to stir up and analyze subsurface material. And while Bennu has a very slight chance of colliding with Earth in 160 years, the mission has already helped refine its orbital predictions, reducing uncertainties for the future. The initial findings from Bennu's samples have exceeded expectations, opening doors to questions we've only just begun to ask. Where did Bennu's parent body form? Could Earth's water or organic compounds have come from asteroids like Bennu? And what secrets will Apophis reveal when OSIRIS-APEX arrives? One thing's for sure, these missions are reshaping our understanding of the solar system's origins and the building blocks of life. Thanks for watching. Don't forget to like, subscribe, and keep looking up because the universe is always waiting for you to explore.